something is wrong with reality. Not wrong in the way a broken clock is wrong, not wrong in a way science will eventually fix. Wrong in a way that the greatest minds who have ever lived, physicists, cosmologists, Nobel laureates, have stared into directly, and then looked away. Because what they found there was not an answer, it was a deeper question, one that may have no end. Tonight, we are going to sit with that question. We are going to travel through the ideas of the people who understood the universe better than almost anyone who has ever lived. Einstein, Hawking, Feynman, Sagan, Penrose, Michio Kaku, Kip Thorne, Oppenheimer, Neil deGrasse Tyson, Brian Cox. We are going to go where their ideas lead, all the way to the edge. And I promise you this, by the time we reach the end of this journey tonight, the universe will feel larger, time will feel stranger, and reality itself will feel like something far more mysterious than the word reality was ever meant to contain. Let's begin. In 1905, a 26-year-old patent clerk in Bern, Switzerland, sat at his desk, not in a prestigious university, not in a laboratory, at a government office reviewing other people's inventions. And in his spare moments, Albert Einstein was quietly dismantling reality. He had not run a single experiment. He had no telescope, no particle accelerator, no data set. He had something rarer, an imagination so disciplined it could see through the mathematics of the universe to what was actually happening underneath. And what he found was this: time is not fixed. Read that again slowly. Time is not fixed. Einstein proved that time moves at different speeds depending on how fast you are moving and how deep you sit in a gravitational field. The clock on your wrist is ticking at a different rate than a clock aboard a satellite orbiting the Earth right now. Not by much, but measurably, verifiably, irrefutably. The GPS system in your phone would give you directions several miles off within a single day if engineers did not account for time dilation, the difference in how time flows between the surface of the Earth and the satellites overhead. This is not a theory waiting to be tested. It is a correction we make, every day, in practical technology. Einstein was right. Time bends. But here is the part that stops people cold. If time moves faster for something in weaker gravity and slower for something near enormous mass, then near an object massive enough, time can slow almost to a stop. And there are objects in this universe massive enough to do exactly that. Before we go any further, if you're finding this journey worth taking, consider subscribing to Sleep and Learn. It costs nothing, it helps more than you know, and there is so much more of the universe left to explore together. Now, let's keep going. In 1974, a 32-year-old physicist named Stephen Hawking received a discovery so disturbing that he spent several days convinced he had made a mistake. He hadn't. For decades, black holes had been understood as pure consumption, objects so gravitationally overwhelming that nothing, not matter, not light, not any signal of any kind, could escape once it crossed the boundary known as the event horizon. They were thought to be perfect traps, silent, eternal, absolute. Hawking proved they were none of these things. By combining quantum mechanics, the physics of the very small, with general relativity, the physics of the very large, Hawking showed that black holes are not completely dark. They glow. Barely, faintly, almost impossibly dimly, but they emit radiation. And because they emit radiation, they lose mass, and because they lose mass, they eventually evaporate. Every black hole in the universe, including the supermassive one at the center of our own galaxy, 4 million times the mass of the Sun, is dying. Slowly, unimaginably slowly, but dying nonetheless. The most terrifying structures in the known universe are mortal. Hawking himself described the moment he realized this as one of the most exciting of his life. He lay awake that night, unable to sleep, mind racing with a discovery he hadn't gone looking for, one that arrived out of sheer mathematical curiosity. And it opened a wound in physics that has not fully healed since. Because if black holes evaporate, something troubling happens to the information that fell into them. Every particle that ever crossed an event horizon carried information, its quantum state, its history, its relationship to the rest of the universe. When a black hole evaporates completely, where does that information go? Hawking initially argued it disappears, destroyed forever, gone. Most physicists found this intolerable. One of the deepest principles of quantum mechanics states that information cannot be destroyed, ever, under any circumstances. This disagreement, known as the black hole information paradox, became one of the longest, most heated arguments in the history of modern physics. It lasted decades. It consumed careers. It still has not been fully resolved. Hawking eventually changed his position near the end of his life. He came to believe the information might escape, encoded within the radiation. But the mathematics of exactly how remains one of the deepest unsolved problems in theoretical physics. Which means, right now, tonight, as you listen to this, the greatest minds in physics are still working on a problem Stephen Hawking spent 50 years circling. That is how hard the universe is to understand. Now we need to go somewhere stranger, somewhere that even the people who built the theory admit they don't fully understand. Richard Feynman once said something remarkable. He said, "Nobody truly understands quantum mechanics. Not students, not professors, not even the physicists who spent their lives building the theory itself." And he wasn't being modest, he was being precise. Quantum mechanics is the most tested, most successful, most accurate scientific theory in human history. Its predictions have been confirmed to an accuracy of 1 part in a billion. It underlies every semiconductor, every laser, every MRI machine, every transistor in every device you have ever touched. The modern world runs on quantum mechanics. And yet, nobody agrees on what it means, what it is actually describing, what is actually happening when a quantum system behaves the way it does. Here is the problem. At the quantum scale, the scale of electrons, photons, subatomic particles, the universe does not behave the way anything in our everyday experience does. An electron does not have a definite position until you look at it. It exists as a cloud of probabilities, a smear of potential locations spread across space. The moment you measure it, the moment any physical interaction occurs that gives you information about where it is, that cloud collapses. The electron is suddenly somewhere. But here's the question that has haunted physics since the 1920s. Did the electron have a position before you looked? Most interpretations of quantum mechanics say no, not in any physically meaningful sense. The electron was nowhere. It was everywhere and nowhere simultaneously. A superposition of possibilities with no fixed reality, until observation collapsed it into one. Einstein despised this. He spent the last 30 years of his life trying to disprove it. He called it spooky action at a distance, a phrase he meant as an insult, referring to the quantum phenomenon of entanglement, where two particles can become linked such that measuring one instantly affects the other, regardless of the distance between them. It bothered Einstein deeply. He believed there had to be hidden variables, some deeper layer of reality where particles did have definite properties, positions, histories, even when we couldn't see them. He was wrong. In the 1960s, a physicist named John Bell devised a mathematical theorem that could test this. And when experiments were finally precise enough to run the test, nature failed Einstein's intuition completely. There are no hidden variables. The universe is, in the language of physics, non-locally real, which means particles do not have definite states independent of observation, and the correlations between entangled particles happen faster than light, instantaneously, regardless of distance. Alain Aspect confirmed this experimentally in 1982. Anton Zeilinger and John Clauser refined it across decades. In 2022, the Nobel Prize in Physics was awarded for this exact work. The universe is not locally real. Sit with that. The universe you live in, the floor beneath you, the air in your lungs, the stars above you, is, at its deepest level, not locally real. Now let us zoom out, far out. Carl Sagan once stood on a stage and showed an image of Earth photographed by the Voyager 1 spacecraft from 6 billion kilometers away. In the image, our planet appears as a single pale blue pixel, a mote of dust suspended in a sunbeam. Sagan said that every human being who ever lived, every empire that ever rose and fell, every act of courage and cruelty and love and grief in all of recorded history happened on that pixel. That image was taken from within our own solar system, not from outside our galaxy, not from outside our galactic cluster, from within our own solar system. Our galaxy, the Milky Way, contains somewhere between 200 billion and 400 billion stars. Our Sun is one of them. The nearest star to our Sun is Proxima Centauri. It is 4.2 light-years away. Light travels at 300,000 kilometers per second. At that speed, it would take 4.2 years to reach our nearest neighbor. The fastest spacecraft humans have ever launched, New Horizons, which flew past Pluto, would take roughly 75,000 years to make that journey. And Proxima Centauri is our neighbor, our immediate next-door neighbor. The Milky Way is 100,000 light-years across. The Andromeda Galaxy, the nearest large galaxy to ours, is 2.5 million light-years away. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years in diameter, and it may only be a tiny fraction of the full universe, which may be infinite. Neil deGrasse Tyson has said something that I find impossible to forget. He said, "The universe is under no obligation to make sense to you. Not because it is chaotic, but because it is vast in ways our nervous systems were never designed to comprehend. We evolved to survive on one small planet, to hunt, to gather, to recognize faces, not to grasp 93 billion light-years, not to feel the weight of 400 billion suns, not to hold in our minds the fact that light currently reaching our telescopes left its source before the Earth existed. The universe has been running for 13.8 billion years. Our species has existed for roughly 300,000. If the history of the universe were compressed into a single calendar year, all of recorded human civilization, every pharaoh, every war, every symphony, every scientific discovery, would occur in the final 22 seconds of December 31st. We are extraordinarily new here. The universe has a biography. It was born, it is expanding, and it will end. Not in fire, not in collision, not in any dramatic apocalyptic sense, in something far stranger, far quieter, far more final. The current scientific consensus is that the universe will end in what cosmologists call the heat death, a state of maximum entropy where all energy has been distributed so evenly across all of space that no thermodynamic work can ever occur again. No stars, no warmth, no motion. No time in any meaningful sense, just an infinite, cold, perfectly uniform darkness. This will not happen for an unimaginable length of time. We are talking about timescales so vast that the current age of the universe, 13.8 billion years, would be a rounding error so small it wouldn't register. Brian Cox has described this trajectory with a kind of calm that itself feels profound. He doesn't catastrophize it. He points to it with the same steady gaze he would use to describe a sunset, as if accepting the end of everything is simply part of understanding everything. But there is something Kip Thorne observed that I find quietly terrifying in a different way. We tend to think of the end of the universe as something impossibly remote, safely distant, a problem for some unfathomably distant generation, if any generation remains. But the universe's fate is already written in its physics. It was determined at the moment of the Big Bang. The expansion rate, the dark energy, the entropy budget, all of it. The ending was decided at the beginning. We are simply living in the middle of a story whose final page was written 13.8 billion years ago. Of all the mysteries we have touched tonight, there is one that many physicists consider the most dangerous to approach. Not dangerous in a physical sense. Dangerous because it sits at the exact boundary between science and something science may not be equipped to answer. The question of consciousness. Not consciousness in the soft, philosophical sense, in the hard, physical sense. Why does experience exist at all? Why is there something it feels like to be you? Why is there an inner world of sensation, thought, memory, and awareness, when from the outside, a brain is simply 3 pounds of electrochemical tissue performing calculations? Roger Penrose, one of the most brilliant mathematical physicists alive, spent decades arguing that consciousness cannot be explained by classical physics, that standard neuroscience, no matter how precisely it maps neural activity, will never explain why experience exists. He proposed, with anesthesiologist Stuart Hameroff, that consciousness arises from quantum processes within microtubules inside neurons, tiny structures where quantum coherence might allow something beyond classical computation to occur. The theory remains deeply controversial. Most neuroscientists are skeptical. Most quantum physicists are skeptical. But here is what makes it impossible to simply dismiss. Penrose is not a fringe thinker. He proved fundamental theorems about black holes that Hawking built upon. He worked with Einstein's mathematics in ways that reshaped modern cosmology. When Penrose says consciousness might require physics we haven't discovered yet, that deserves to be taken seriously. Because here is the alternative. If consciousness is entirely classical, entirely explainable by neurons firing, then at some level, you are a very complex calculator. Your sense of wonder right now, your awareness of this moment, your feeling that any of this matters, all of it would be an illusion generated by physics, a simulation of significance running on biological hardware. And that answer has its own terrifying implications. In 2003, philosopher Nick Bostrom published an argument so clean and so unsettling that physicists, cosmologists, and technologists have been unable to fully escape it since. He called it the simulation argument. It goes roughly like this. Either civilizations almost always destroy themselves before developing the computing power to create realistic simulations of conscious beings, or they develop that power but almost universally choose not to use it, or we are almost certainly living inside a simulation right now. Michio Kaku has spoken about this with characteristic precision. He doesn't fully endorse the simulation hypothesis, but he refuses to dismiss it, because here is the unsettling part. If a sufficiently advanced civilization could run simulations of conscious minds, and ran many of them, then simulated minds would vastly outnumber real ones. And if you cannot tell from the inside whether your experience is real or simulated, which, so far, nobody can, then the probability calculation is deeply uncomfortable. Neil deGrasse Tyson gave the probability of the simulation hypothesis being true as 50-50 at a conference, in public. Elon Musk has said he believes the odds that we are in base reality are roughly 1 in billions. These are not people prone to idle speculation. The more troubling version of the argument is what physicists call the fine-tuning problem. The fundamental constants of the universe, the strength of gravity, the charge of the electron, the cosmological constant, are tuned to values that permit complex structures, chemistry, stars, planets, and life with a precision that should statistically be almost impossible by chance. Change the gravitational constant by a fraction, the universe collapses before stars form. Change the cosmological constant slightly in the other direction, matter disperses before galaxies coalesce. The universe appears to have been dialed in, calibrated. Whether that points to a simulation, to a multiverse, to a deeper physics we haven't discovered, or to something beyond the reach of science entirely, nobody knows. But the question itself feels important, because if the universe was somehow set up for something, the question of what that something is becomes the most important question anyone has ever asked. We've traveled far tonight, through time dilation and dying black holes, through the uncertainty at the heart of matter, through the incomprehensible scale of space, through the heat death of everything, through the mystery of consciousness, through the possibility that none of it is quite what it appears. And I want to stop here, close to the end, and simply tell you what the people who understood all of this most deeply felt. Albert Einstein, in the final years of his life, described a sensation he called the cosmic religious feeling, not tied to any theology, not tied to any doctrine, but a profound, wordless sense of awe at the order and vastness of the universe, an emotional response to the fact that it was comprehensible at all. He said this feeling was the most powerful motivation for scientific research. Richard Feynman said that the beauty of a flower was not diminished by understanding its biology, that knowing the mechanisms of how light scatters in a petal added dimensions of wonder rather than removing them. He described science as an expansion of imagination, not a reduction of mystery, but a multiplication of it. Carl Sagan wrote that we are a way for the cosmos to know itself, that the atoms in our bodies were forged in the cores of ancient stars, that we are, in the most literal sense, made of star stuff, and that when you look up at the night sky with wonder, the universe is looking back at itself through the instrument of you. Stephen Hawking, who by every measure of ordinary physics should not have lived past his late 20s, who spent over 50 years thinking through the most extreme environments in the universe from a wheelchair, using a voice synthesizer to share ideas that reshaped our understanding of time and space, said near the end of his life that the greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. And J. Robert Oppenheimer, the man who built the atomic bomb, who watched the first nuclear test detonate at Trinity and said, "Now I am become death, the destroyer of worlds," spent the rest of his life haunted by the question of what science is for, what knowledge is for, what the point of understanding the universe is if that understanding can also be weaponized against it. That question has no clean answer, but the fact that Oppenheimer asked it, deeply, painfully, for the rest of his life, says something important about what it means to truly reckon with what we know. I want to leave you with something that I think about often, something that sits quietly at the edge of everything we've discussed tonight. In 2015, Kip Thorne watched a computer simulation of what a black hole would look like if you were near it. The simulation was built for the film Interstellar, which Thorne produced and consulted on. The visual effects team built the simulation to his precise specifications. The relativistic equations, the light bending, the accretion disk, all of it correct. And what appeared on screen was not what anyone expected. The light from behind the black hole bent around it in a way that produced a luminous halo, not just above and below, but wrapping completely around the event horizon. A ring of light. The effect was so unexpected that Thorne wrote 2 scientific papers about it, papers based on images generated for a movie. A Hollywood visual effects team had accidentally computed a new prediction of general relativity. And in 2019, the Event Horizon Telescope, a global network of radio observatories linked together to form a telescope the size of the Earth, captured the first real image of a black hole. The image showed exactly what the simulation had shown, a glowing ring of distorted light surrounding darkness. The real universe looked like the movie, because the movie was built from the real equations, because the equations were real. Einstein's field equations, written in 1915, predicted the image that appeared on screens in 2019. 104 years later, before photography existed that could capture it, before technology existed to attempt it, before the concept of a black hole was even fully accepted, the mathematics knew before we did. And that, perhaps more than anything else, is what makes this story so extraordinary. Not just that the universe is vast, not just that it is strange, not just that it bends time and erases information and hums at the edge of black holes and creates consciousness somehow, somewhere, in 3 pounds of tissue, but that it is legible. That somewhere along the way, a universe that had no obligation to make any sense became describable in mathematics so precise that we could write equations on paper in 1915 and predict an image we would photograph in 2019. That the same universe that will end in cold silence 13 trillion years from now produced for one brief chapter creatures capable of understanding that, creatures capable of writing it down, capable of lying quietly in the dark tonight and feeling the weight of it. Brian Cox once said that we are the universe contemplating itself. And I don't think that's poetry. I think that might be the most accurate description of what we are that anyone has ever offered. The physicists whose ideas we followed tonight, Einstein, Hawking, Feynman, Sagan, Penrose, Kip Thorne, Michio Kaku, Brian Cox, Neil deGrasse Tyson, Oppenheimer, did not agree on everything. They argued, sometimes bitterly. They changed their minds, sometimes reluctantly. They made mistakes, they revised, they started over. But they shared something, a willingness to follow the question wherever it led, even when it led somewhere uncomfortable, even when it dissolved assumptions they had built their careers upon, even when the answer turned out to be stranger, darker, and more beautiful than the question they started with. That is the invitation the universe extends to everyone who looks up. Follow the question, even when it gets strange, especially when it gets strange. Because the strangeness is not a sign that you've gone wrong. It is a sign that you've gone deep enough to find something real. Tonight, the universe is exactly what it has always been. Vast, indifferent in scale, precise in its laws, mysterious at its foundation, and somehow aware of itself through you. Sleep well.